Hello ECO101, this is your last recorded tutorial for the semester, and in this tutorial video, we will be working on the two last topics of the semester, which are externalities and oligopoly. So as usual, I recommend that you read the questions, pause the video, and attempt to solve the problems on your own before pressing play and watching my solutions. So let's get started with the first exercise. Suppose that the ECO101 vaccine is a one-dose vaccine that protects against an infectious brain disease. The immunity that you get from this vaccine is long-lasting, and cases where you are infected after receiving the vaccine are very rare. Vaccinated individuals not only protect themselves, but they also protect others around them by reducing transmission of the disease, which results in a very large social benefit from vaccination. However, this also leads to free riding by some individuals who benefit from collective protection, which we also call herd immunity, and those individuals, they skip taking the vaccine for themselves. You work as a health economist for the Ontario Ministry of Health, and you find that the social benefit of vaccination, which is the collective benefit in dollars that the entire society gets from one extra individual who gets the vaccine, is given by this function. Q is in millions of doses received. Remember that this is a one-dose vaccine. And we also know that the private benefit of vaccination, the personal benefit also in dollars, that one additional person who gets the vaccine for ECO101 is given by this formula. And the last information that we have is that the private cost of vaccination, which is the manufacturer's cost of producing one dose of this vaccine, is constant at $20 per dose. So that's all the information that we have. Let's now read the first question. You work for the health ministry and they ask you to estimate the value of the external benefit of vaccination, which is the benefit that one additional vaccinated individual provides to others around them by improving community immunity against ECO101 when 6 million Ontarians are vaccinated. So now I would recommend to pause the video and try to solve this problem by yourself before pressing play and watching my solutions. Alright, so you are back. Let's look at the information that we have again. The first thing to acknowledge, of course, is that this is an externalities problem. We can see it in this sentence, what it says that we have free riding from individuals who benefit from collective protection. So this is basically, we are talking about a positive externality, so a marginal external benefit. So since we have a marginal external benefit that is not internalized by actors in this market, it means that the market equilibrium will be different from what is the social optimum. In the other equations that we have, they also give us important information. They have different name from what you might be familiar with. For example, the social benefit of vaccination. If you see the definition, this is the collective benefit that the entire society gets. So we are basically describing a marginal societal benefit from vaccination. And the other equation that we have, the second one, the private benefit of vaccination, which is defined as the private benefit that one additional vaccinated person gets from getting the vaccine. Well, this is, of course, the marginal private benefit according to this definition. And the last information that we have, the pharmaceutical company's cost of producing one additional dose of the vaccine. This is, of course, the marginal private cost of producing a vaccine. And in part A, what we are asking about is the external benefit of vaccination, which is the benefit that one additional vaccinated individual provides to other people around them by the fact that they increase herd immunity. Well, this is, of course, the marginal external benefit of vaccination. So don't get too confused by those new terms. They are in fact the same ones that you know according to the definitions. We just need to apply them and find what is the marginal external benefit when quantity is 6 million doses. So we want first the total benefit the marginal societal benefit from vaccination, which we call the social benefit of vaccination. And we know that this is the sum of the private benefit of vaccination, so the marginal private benefit. And to that, we need to add also the value of the external benefit, this positive externality, which we call the external benefit of vaccination. So we're saying marginal societal benefit is equal to marginal private benefit plus marginal external benefit. And the value that we want to find is the marginal external benefit of vaccination when 6 million people are vaccinated. So this last term is what we want to solve for. So the external benefit of vaccination is simply the societal benefit of vaccination minus the private benefit of vaccination. And we already have formulas for both of these terms. We know that external benefit of vaccination is the societal benefit of vaccination, which is 90 minus 5Q, according to the formulas that you have at the beginning of the problem. And we also have the private benefit of vaccination, which is 90 minus 35 times the quantity of people vaccinated divided by 6. So for this particular situation, we know that we are not going to get simply a number for the external benefit of vaccination, which is the marginal external benefit. This time we are going to get a function for the external benefit of vaccination, and it is going to depend on Q, the number of people who are vaccinated. So just simplify this term, 90 minus 90 gets eliminated, then minus 5Q plus 35Q over 6. And we get that the external benefit of vaccination is equal to 5 times the number of people who received vaccine doses divided by 6. So this function in general gives me the value of the marginal external benefit depending on the number of people who have received a vaccine. So it depends positively on the number of people who receive the vaccine, which means that more people being vaccinated increases the value of this external benefit of vaccination, which makes sense because more people having received the vaccine means that herd immunity is even stronger. But our job is done here. We just need to find the value of the external benefit of vaccination when quantity is equal to 6 million people. So we just need to substitute this value inside the external benefit function that we already built. 5 times 6 million people having received the vaccine divided by 6. And this gives us the external benefit that the last person, the 6 millionth person who received the vaccine, is transferring to others by increasing herd immunity, which is in this case a $5 positive externality that the last individual gives to other people by improving collective immunity. And we are done here. This should be our final answer. Let me just very quickly just illustrate this problem in a graph. So as usual, I want to have quantity on the horizontal axis, so millions of doses. And on the vertical axis, I'm going to put all the benefits and all the cost in dollars. First, we know that the marginal cost of production is simply equal to $20. It is constant. This is the private cost of vaccination. We have a demand function, the marginal private benefit function, which we call the private benefit of vaccination, which is actually lower than the entire society's benefit from vaccination. And how much lower is the private benefit of vaccination compared to the societal benefit of vaccination? Well, it is exactly lower by the value of this function, which depends on Q. So when Q is equal to 0, nobody has been vaccinated. Both functions are exactly equal, which also makes sense because very few people being vaccinated increases herd immunity by very little. So like I said, our societal benefit of vaccination is going to share the same intercept as the private benefit of vaccination. But the gap between societal benefit of vaccination and private benefit of vaccination is going to keep increasing with people receiving more and more doses. The value that we just calculated is for 6 million people being vaccinated in the province. And we found that the difference between the two was equal to $5 external benefit per dose. So this external benefit of vaccination is going to keep increasing with more people having received the vaccine. So that's it. We are done for this part of the problem. Let's go to part B. All right, so now that we have all of those functions, we can use them to find the equilibrium and the optimum level of vaccination, which is this question in here. First one asks what percentage of the population, which is 50 million people, is vaccinated at the market equilibrium. And the second one asks how many more individuals should receive the vaccine beyond this market equilibrium to achieve the optimum level of vaccination for the entire society. So again, just a reminder to pause this video, try to solve this by yourself, and then come back and see my solutions. All right, so we have here a bit more information. First of all, we know that the total population, so the maximum quantity that we can have in this market is 50 million people. And we have to find first the market equilibrium and then the optimum level of vaccination, which are two different concepts. So let's do that. Let me first copy the graph that we had before. And let's start with the equilibrium quantity first. So we want to find the level that the market is going to give us given the private benefits and the private costs only, which will reach when private actors in this market, private individuals and private firms, don't internalize this external benefit in their decisions. So we are going to get the market equilibrium exactly here as usual, where private benefit intersects private costs. So demand is equal to supply. So we just need to solve for quantity in this condition where demand is equal to the supply. So let's start putting this in place. We are saying that private benefit of vaccination without taking into account the externality has to be equal to the private cost of vaccination, which is simply the marginal cost of production. And the private benefit of vaccination is simply our marginal benefit function, our demand function, 90 minus 35 times Q, which is going to be the market quantity, divided by 6. This is the function that was given to us at the beginning. And we also know that it costs the manufacturer $20 to produce one dose of the vaccine. We need to solve for quantity, so let's maybe just send numbers on the same side, multiply everything by -1 as well. So 35 times the market quantity we're looking for divided by 6 is equal to 70. We multiply by 6 both sides and we divide by 35 both sides. The market quantity, the equilibrium that we are going to get when only private costs and private benefits are taken into account, is equal to 12 million doses received by individuals. So 12 million people vaccinated. So we have found the value that we were looking for in here, where demand is equal to supply. We have 12 million doses received, but what we actually wanted is the vaccination rate. So that should be easy to compute because we have the population already. 12 million people have received the vaccine, but the province's population is 15 million people. So in percentage, this is 80% of the population being vaccinated at the market equilibrium, where marginal private cost is equal to marginal private benefit. And in the second part of this problem, we have to solve for the optimal level of vaccination instead. And the optimum refers to a different concept. We're looking for the quantity that will be socially efficient. So we need to set our social benefit of vaccination instead of the private benefit of vaccination equal to the private cost of vaccination. So you can see where the number of people vaccinated is efficient for the entire society. It is going to be at this intersection here, like I said, between societal benefit of vaccination and private cost of vaccination. This is what is really optimal and most efficient for the entire society. So we want to solve for this optimum point. This time we are going to set our social benefit of vaccination, which is the marginal societal benefit, equal to the private cost of vaccination. Because the societal benefit of vaccination takes into account the positive externality that people getting vaccinated give to the entire society. but we do need to use our other function for the societal benefit of vaccination, which is higher than the private benefit of vaccination. So we have 90 minus 5 times the quantity that we need to solve, which is the quantity that is really efficient for the entire society. We need to set this equal to private cost of vaccination, which is the marginal cost, $20. And this algebra problem is even easier to solve. We subtract minus 90 both sides, and then we divide by minus 5 both sides. So we get that the quantity that is really optimal is when we have 14 million people in the province having received the vaccine. So we have 14 million doses instead of 12 million doses. So this is the quantity in here that we were looking for, where private cost of vaccination equals the societal benefit of vaccination. Now we can finally conclude this question. We know that the difference between the two is $2 million. So the difference between what is most efficient for society and what the market is going to give you when only private costs and private benefits are taken into account is equal to 2 million doses. We have a 2 million doses deficit that is actually going to create a deadweight loss in society because we have not internalized yet the marginal external benefit of people getting the vaccine and increasing community immunity. So that's it for this part of the problem. Hopefully you got this right. Let's do the other part of the problem. For this part of the problem, we will actually have to compute the value of deadweight loss because we will have to compare it to a policy. So let's first read the question. Suppose there's a vaccine mandate that requires everybody to receive this vaccine, and we want you to compute the reduction in deadweight loss that results from everybody receiving the vaccine. So you can pause the video again and try to solve this by yourself. Alright, so this time we are given a quantity that is mandated. This is equivalent in this case to a quota, what we call a binding purchase quota. This is a minimum amount of doses that has to be received by individuals. I'm going, as usual, to use a graph to illustrate what's happening in this market. And like I said, this is a binding purchase quota where the government mandates quantity exchange to be 50 million doses. And this is by law the quantity that is going to be exchanged, giving this binding purchase quota, this vaccine mandate. The entire population of 50 million people is going to be vaccinated. But before we even compute what effect this quota is going to have in this market, let's just start first with deadweight loss that is associated with the equilibrium quantity that is going to be exchanged in this market, which we said just previously that this is when 12 million people receive a dose of vaccine. But like we said, this is not optimal for society because we are going to have a marginal external benefit of vaccination, which means that quantity is way too low compared to what is the social optimum. And deadweight loss is simply all of this social surplus that is low due to market quantity being way too low and not incorporating the marginal external benefit of vaccination. We know that if 2 more million people were vaccinated at the social optimum, then we would get this additional area of surplus that is between the social benefit of vaccination and the private cost of vaccination. So our deadweight loss at the market equilibrium of 12 million people being vaccinated is simply the area of this little gray triangle that is in between the social benefit of vaccination and the private cost of vaccination, and between the optimum quantity and the equilibrium quantity. So the base of this triangle is simply the difference between those two values, 14 million people being vaccinated at the social optimum minus 12 million people being vaccinated at the market equilibrium. And the height of this triangle is simply the value of the external benefit of vaccination at the market quantity. So the height of the deadweight loss triangle, this is just the value of our external benefit of vaccination, the marginal external benefit at the market quantity equal to 12. And we have an entire function that we built for that in part A. We said that the function for the external benefit of vaccination is 5q over 6, which was just the difference between the social benefit of vaccination function and the private benefit of vaccination function. So you could also just compute the difference between those two functions. But I'm just going to use the function that we built. So 5 times the quantity, 12 million doses, divided by 6. And this gives us the external benefit of vaccination for the last person who receives the vaccine at the market equilibrium. So this last person being vaccinated gives a $10 external benefit to the society by increasing herd immunity. And the society could receive more surplus by increasing the number of vaccines. But, well, this is not the market equilibrium. So this is why we have deadweight loss. So let's compute the value of deadweight loss at the market quantity, just the area of a triangle whose base is 2 million doses missing to get the optimum quantity exchange. Multiply this by the height, which is just the external benefit of vaccination, $10. That we divide by 2. And this gives us a deadweight loss that is equal to $10 million at the market equilibrium. And this is, of course, a deadweight loss if the government doesn't intervene in this market. And well, as we see, it actually does, as there is this vaccine mandate that forces 15 million people to receive the vaccine. And this is, like I said, a binding minimum quota at the population number. And we'll have to do another computation to see if this is more or less efficient than what the market would give you without government intervention. Because you may see that this quota is also going to introduce deadweight loss in the market. And this is because, as you may see, the government sets a binding quota that is higher than what is the social optimum. So the government is forcing some amount of vaccination where private cost of vaccination is higher for those individuals than the entire societal benefit of vaccination. So we are creating at the same time some deadweight loss because of that additional 1 million doses received above what is socially optimal. And we want to compute the value of this deadweight loss at 15 million people being vaccinated under the mandate. And you can imagine that this is going to be the area of this triangle that is between private cost of vaccination and social benefit of vaccination for those extra 1 million people vaccinated above the 40 million doses that are socially optimal. So this is also a simple calculation. It's going to be the area of a triangle again, and the base is going to be the difference between the quota quantity, so 50 million people vaccinated, the entire province, minus what is the social optimum, which is 14 million people vaccinated when social benefit of vaccination is equal to the private cost of vaccination. And the height of this triangle is simply the difference between the private cost of vaccination, which is always constant at $20 per dose produced, and the social benefit of vaccination at the quota quantity, which is 50 million people being vaccinated under the quota. So for this second part, the social benefit of vaccination, we have already a formula for that was given to you. So 20, the marginal cost, minus the function for social benefit of vaccination is 90 minus 5 times the amount of doses. So that's the social benefit of vaccination for the last person being vaccinated under the quota. And we have everything to compute the value of deadweight loss at 50 million people, the entire population. So the area of a triangle whose base is 1 million doses, the difference between the quota and the optimum, times the height, which is the difference between the marginal cost of production and the value of social benefit for the last person being vaccinated, which is equal to $15 under the quota. So we need, of course, to divide this by 2. And that's going to give us the deadweight loss for the vaccine mandate, which you calculate and it's equal to $2.5 million when everybody, the entire population, gets vaccinated. And that's the analysis to do in here. It is to compare the value of deadweight loss when there isn't a government intervention and when there's this vaccine mandate. And as you can see, dead weight loss is way lower under this quota than what dead weight loss is if the government doesn't intervene and just 12 million people get vaccinated at the market equilibrium, where we are not taking into account the fact that an individual being vaccinated creates a positive externality by increasing collective immunity. So we can just finalize this exercise. We are just going to compute the difference between those two dead weight losses. So $2.5 million under the vaccine mandate minus $10 million, which is the dead weight loss under the market equilibrium. And in conclusion, with this vaccine mandate, the government reduces dead weight loss for the entire society by $7.5 million. And at least in terms of efficiency, in terms of costs and benefits for the entire society, we can see that this policy is actually successful, and at least partially. We'll see that we might be able to do better in the next part of the exercise. Okay, so this is the last part of the problem. Suppose now that the government is considering replacing this quota with a cash for shots program that would offer people money to get vaccinated with the ECO101 vaccine. And we want you to compute the optimal payout to give for every dose of the vaccine. You also have to say what the vaccination rate will be, what will be the cost of the program for the government, and also how is this going to change dead weight loss for the entire society. So give it a try. All right, good. So welcome back. Hopefully you got this right. I'm first, as usual, going to copy my graph so I can explain things better. First thing that we want to find is the optimal payout. And as you've hopefully realized, this is actually a subsidy that the government gives to consumers. We also have to find the cost of the program for the government, which is also government surplus, which will be negative, of course, because this is money getting out of the government's pocket. And the last thing we have to find is dead weight loss, so we can compare to the market equilibrium and also to the vaccine mandate. All right, so the first part is the most important, but it is not very complicated. The optimal value of the subsidy that you have to give to people or even to firms, to be honest, in this case, it doesn't make a difference. The optimal value of the subsidy, we can see that it is the external benefit of vaccination at the social optimum, right? It is the gap between the social benefit of vaccination and the private benefit of vaccination at 40 million doses, which is what is most efficient for society. So this external benefit of vaccination at the optimum, this should be the subsidy that the government gives to consumers, or as I said, it could also be to firms, so that it restores maximum efficiency. Doing that ensures that we internalize this externality because giving that amount of money to people increases private benefit of vaccination exactly by the amount of the externality. So we are going to reach what is the social optimum. And as I said, we could also be given this subsidy to manufacturers of the vaccine, and we would also get the social optimum. What is important is that your subsidy is always equal to the marginal external benefit at the social optimum. So we are going to set our subsidy equal to the external benefit of vaccination at a quantity equal to 14 million people getting the vaccine. And again, remember that we've built an entire function for the external benefit of vaccination. We did this in part A, and this was equal to 5 times the number of doses being given, which at the optimal is 14 million, and we divide this by 6. This is, remember, simply our external benefit function, and when you compute this value, you find that this optimal subsidy is given to people $11.66 in exchange for receiving their dose of this ECO101 vaccine. And as I said, this will ensure that we restore efficiency. This will shift the private benefit of vaccination function up exactly by the external benefit at the optimum. So I'm just shifting my private benefit function by the optimal amount of the subsidy, $11.66. And when you do this, you can see that the equilibrium now is exactly at the optimal quantity, what is more efficient for society when 14 million people are being vaccinated. So the job is done. We get exactly what we wanted. We get the optimum. We get this quantity that is most efficient for society. But of course, what we want is the vaccination rate. But this should be pretty simple as well because we have the population. So we're saying that with this optimal subsidy, 14 million people are going to be vaccinated and the entire population is 15 million people. So with the optimal subsidy, we get that 93.3% of the population gets vaccinated. So as you can see in this case, it is not necessarily 100% of the population being vaccinated that is most efficient. The reason being that we have a private benefit of vaccination, we have a marginal benefit that is decreasing, meaning that some people have a marginal benefit that is lower than others. And even with the externality, at some point you have that the societal benefit of vaccination is lower than the private cost of vaccination. So even with those herd immunity effects, we can see that in terms of costs and benefits, 93% is what maximizes efficiency. And of course, since we are saying that this is maximum efficiency, our dead weight loss at the social optimum, this is equal to 0. We are at the optimum point where private benefit of vaccination and social benefit of vaccination are equal to the private cost of vaccination. So we have no dead weight loss in here. And we do have one more thing to compute in here, which is the cost of the program for the government. So we want to find what is government surplus with this subsidy. And this is just the area of this rectangle in here, which is just the number of doses received at the optimum, which is 14 million doses with this subsidy, multiplied by the subsidy, which is $11.66 per dose that the government pays to individuals in order to restore efficiency. And we have, of course, negative government surplus. These are expenses of $163,240,000 in order to pay this subsidy to people in exchange for getting vaccinated. So that is it. We are done for this exercise. Okay, great. I'm sure you did very good on this exercise. So let's do the next one. Let's read the question first, and then I recommend that you pause the video and try to solve it by yourself. So the Canadian airline industry is largely dominated by two airlines, according to Canada's Competition Bureau. Suppose that these two airlines are named Aero Canada and EasyJet. Both of these companies, they decide on the number of plane tickets that they are going to sell simultaneously. And Canadian customers, they see no difference between flying with either of the two airlines as the services are perceived as being identical. In the second paragraph, we have more information about the cost. Both companies, they have yearly expenses of $2.3 billion for maintaining their planes, advertising, and paying salaries to the permanent employees. And also it costs both airlines $60 for every passenger that they service. And in the last paragraph, you are given a demand function for airline tickets. And there's one last assumption, and that's price adjusts to sell all tickets according to this demand function. So that's all the information that we have. Let's read the first question. We first have to find the number of passengers that are transported daily by both airlines. And we also have to find the price for the plane tickets at the Nash equilibrium. So I'd suggest you pause the video and try to solve this by yourself. All right, so let's do this together then. First of all, of course, this is a duopoly question. And also, you've probably noticed that these are all the assumptions of a Cournot duopoly, especially that both companies, they decide on quantity that they sell simultaneously. So they don't choose prices as in a Bertrand duopoly, but they choose quantity as a Cournot duopoly. So that's good to know. And then let's just for a second analyze the information that we have about the cost. Of course, the yearly expenses of $2.3 billion for maintenance, for advertising, and paying salaries to permanent employees. These are, of course, fixed costs of production because they don't change with the number of plane tickets sold. But then in the second sentence of the second paragraph, where it says that it costs both airlines $60 to transport one passenger, then this is of course a marginal cost of production because it increases with the number of customers served. And then we can do just one more thing while we're here. This demand function that we have is a quantity function, and it might be useful to invert it right away, as we might need the inverse demand function to use the twice as steep rule to find the marginal revenue function. So if we invert this, we're going to get 61,200 divided by 20, which is 3,060, minus the quantity demanded divided by 20. And as I said, this inverse demand function instead of the quantity function is going to be useful in order to find marginal revenue quickly. So let's start solving this first part of the exercise. We have to find quantity for Aero Canada. We also have to find quantity for EasyJet. And at last, we have to find the price for plane tickets. And as I said, well, this is a Cournot duopoly. So firms, they decide on the quantities that they are going to sell. So let me just rewrite the demand function that we have. This is my inverse demand function that I just found before. And the quantity that we have here in the demand function is the market quantity. And this is a duopoly market. So we have two firms producing some quantity at the same time. So total quantity is the quantity that Aero Canada produces plus the quantity that the other company, EasyJet, produces. So that the price is given by the demand function, and it depends on how many tickets Aero Canada sells and how many tickets EasyJet is going to sell as well. So this is just rewriting my inverse demand function, but as a function of both quantities. Okay, so we need to find first the quantities at the Nash equilibrium. So we'll need to find the best response functions for both firms. But the profit maximization rule is the same as usual. Let's start with Aero Canada. Let's say this company is going to set as usual its marginal cost of production equal to its marginal benefit that it earns, so the marginal revenue. And this is the condition that maximizes profit. For the first part, the marginal cost of production, we already have. It is $60 per unit, but we don't have yet the marginal revenue. So this is going to be our first step. So I'm going to divide this into clear steps. Step number 1, starting with the first firm, Aero Canada. We are going to find that function, the marginal revenue that Aero Canada earns in this market. And we are going to use the same shortcut as usual. We are going to use the twice as steep as the demand function, but the demand function that depends on quantity that Aero Canada produces. This is going to be the variable for this company, and this is going to be our shortcut to find the marginal revenue function faster. So let me just first rewrite very quickly the demand function that we have. P is equal to 3060 minus the quantity that Aero Canada produces divided by 20 minus the quantity that EasyJet produces divided by 20 as well. So we are going to use the twice as steep rule as usual. But the important thing to understand here is that the only variable that Aero Canada can change is its own quantity. The other variable, the quantity that EasyJet produces, is not really something that Aero Canada controls. So we will treat this quantity as given. It's just a number because Aero Canada cannot change this variable. And knowing that, let's write our marginal revenue function for Aero Canada. So we're going to keep the same intercept, 3060, and then it'll just be here where we use our twice as steep rule. We will multiply the slope of this function by 2, so we get 2 times the quantity that Aero Canada produces divided by 20. And like I said, this other quantity that EastJet produces, we are going to treat this as a constant. It might as well be a part of the intercept. We will not multiply this quantity by 2 because it is just given for Aero Canada. It is not a variable that this company can change. So again, remember, if you want to use this twice as steep shortcut to find the marginal revenue for Aero Canada instead of using calculus, then you have to multiply only the quantity of Aero Canada by 2 and not the quantity of the other firm. But we're done for step number 1. Let's do step number 2, where we'll set marginal cost equal to marginal revenue for Aero Canada. So this is going to be exactly what we'll do. On step number 2, we will set marginal cost of Aero Canada equal to its marginal revenue, because this is the usual profit maximization condition. But in this case, it would also give us a best response function or a reaction function for Aero Canada. So this is going to give us the best reaction possible in terms of quantity produced by Aero Canada, given what the other firm is doing. So given what quantity EastJet decides to produce. And we're actually able to do this now because we have both marginal cost and marginal revenue. Marginal cost is equal to $60 per unit supplied. And marginal revenue function, we just found this with the twice as steep rule, 3060 minus quantity that Aero Canada produces divided by 10. We got this with the twice as steep rule. And then we kept the other quantity as fixed for EastJet. And this is almost it. This is our best reaction function already because we have the profit maximization condition and both variables in one equation. But we will now solve for the quantity that Aero Canada will sell in order to have this best reaction function. We can start by sending the quantity that Aero Canada sells on the left hand side and send the numbers on the right hand side. So we have quantity that Aero Canada sells divided by 10 minus 60, so 3000, minus the quantity that EastJet sells divided by 20. And one more step to solve for this quantity, we'll multiply both sides by 10. So we get our best reaction function. The quantity that Aero Canada chooses as its best response is equal to 30,000 minus the quantity that EastJet chooses divided by 2. This is the best reaction of Aero Canada to what EastJet produces. So we are done for step number 2. We have Aero Canada's best response. Step number 3 is going to be to get the best response function for EastJet as well. So one thing to do in here is to go back to step number 1 to find the marginal revenue function for EastJet as well, and then go to step number 2 and set marginal cost equal to marginal revenue for EastJet as well. But it is only necessary to do those steps again if the marginal cost for EastJet is different from the marginal cost of production for Aero Canada. So I'm saying that if both firms have different marginal costs of production, you will need to set those conditions again. But in this particular case, we have a market that is symmetrical. So we have that marginal cost for EastJet is exactly the same as the marginal cost of Aero Canada. So this is what we call a symmetrical problem when both firms in a duopoly have exactly the same marginal cost of production. Then in that case, you don't need to do those steps back again. You can just copy the best reaction function that you found for one firm in order to get the best response function for the other firm. The only thing that you need to do if this problem is symmetrical is to switch the variables in the best response function, because both firms are going to best respond in a symmetrical way. So I will just take the same function for EastJet that I found for Aero Canada and just switch the values. That way the problem is faster to solve. The best response quantity for EastJet is also equal to 30,000 minus the quantity that Aero Canada produces divided by 2. So like I'm saying, these are exactly the same best response function for both firms. I just switched the variables. And now that I have best response functions for both firms, I can go to step number 4, which is going to be to solve for the Nash equilibrium. I know how both firms are going to best respond to the other, so I can solve for this Nash equilibrium, which is going to give me the equilibrium quantity for Aero Canada and the equilibrium quantity for EastJet when both firms are best responding to each other. And in this step number 4, I can actually add a third equation. So if we have that this duopoly is symmetrical, meaning that both firms have exactly the same marginal cost of production, we can add a condition, and it is that since both firms are symmetrical, they are going to produce exactly the same unit at the Nash equilibrium. So Aero Canada and EastJet are going to sell exactly the same number of tickets. So the problem is mathematically very easy to solve. I can just take any of those two best response function. Let me take the one for Aero Canada, which is 30,000 minus the quantity that EastJet produces divided by 2. And now knowing that both quantities are equal at the equilibrium, I can just replace the quantity for EastJet by the quantity for Aero Canada. So this is going to give me just one equation with one variable. So the quantity that Aero Canada produces is equal to 30,000 minus the quantity that EastJet produces, which is the same one as Aero Canada produces, divided by 2. And the algebra right now should be very easy to do. I can just set quantities on the left-hand side. So 3/2 times the quantity that Aero Canada sells is equal to 30,000. And I'm practically done. I can multiply both sides by 1.5. So I get that the quantity that Aero Canada sells is equal to 20,000 tickets at the Nash equilibrium. We know that at the Nash equilibrium, they produce exactly the same amount. They are going to sell exactly the same number of tickets. So EastJet also serves 20,000 passengers at the Nash equilibrium. And that's it. That's the first part of the answer. We have the number of tickets sold by both companies at the Nash equilibrium. The only thing that we are missing is the equilibrium price. But the price, we always get it with the demand function. So we can use our inverse demand function to find the equilibrium price now that we have quantities. So that's 3,060 minus total quantity sold in the market, which is the quantity that Aero Canada sells, plus the quantity that EastJet sells. That we divide by 20. That's just our demand function. And we know these quantities now. So 3,060 minus 2 times 20,000. So 20,000 tickets sold by Aero Canada and 20,000 sold by EastJet as well at the equilibrium. We divide by 20. So we just need to calculate this value and we get that the price at the Nash equilibrium, given these quantities and given the demand function, is equal to $1,060 for every ticket. And it is, of course, the same price for both companies, as this is a Cournot duopoly, so firms might have different quantities, but at the end they have the same price. That's it. We're done for part A of this problem. We can now solve part B. Okay, so this second part is actually much easier. It is only computations that you know already how to do. We want to find the yearly profit for both airlines. We also want to find the yearly total producer surplus for both companies. And we have to find yearly consumer surplus at the Nash equilibrium. And I suspect that this is actually very easy for you to do. The profit for Air Canada, which is going to be exactly the same as EastJet because this is a symmetrical problem. We want it in annual terms, so we're just going to multiply everything by the number of days, because what we just found is the daily number of tickets that are sold by the airlines. And the rest of the profit should be very easy. we're going to multiply the price, $1,600 per ticket, times the number of tickets sold by an airline, which is 20,000 daily passengers. And we're going to subtract all the variable costs. So I'm just going to multiply the marginal cost of serving one customer times the number of customers that the airlines are going to serve at the national equilibrium. There's one thing left, and that is the fixed cost of production. So I need to subtract the fixed cost of production, which was given at the beginning. That was $2.3 billion of fixed expenses. So that's it. That's the simple computation in here. If you compute this, you get that the yearly profit for Aero Canada is equal to $5 billion. And like I said, well, this should also be equal to the yearly profit for the other company, EasyJet. That should have been pretty easy for you. So let's find the second thing, which is total producer surplus. So we need to add surplus for both companies. So let's start by finding producer surplus for one company, let's say Aero Canada. And there's a very simple shortcut once you have the profit. The difference between producer surplus and the profit is simply the fixed cost of production. So to get the producer surplus for the company, you just have to add to the profit the fixed cost of production. Right? You remember this? This is because the definition of producer surplus is simply the total revenue minus the variable cost. So really the only difference with the profit is the fact that producer surplus doesn't have the fixed cost of production. So we are just here adding the fixed cost in order to get just total revenue minus variable cost. And we get that the producer surplus for one company is $7.3 billion for a year. And this is also, of course, the producer surplus for the other company, for EasyJet, as this is a symmetrical problem. So we get that total surplus is 2 times $7.3 billion, the producer surplus that one company gets. So for the entire market, producer surplus is $14.6 billion for a year. So if you want to find the producer surplus using the typical way, remember that this is the difference between the price and the marginal cost of production for all quantities produced. So for one firm, it might be this area in here in green. Let's say that's for Air Canada. And then for the other firm, it is going to be the second area in blue. So this is going to give you the sum of the producer surplus, and it should give you also the same result as adding the fixed cost to the profit. All right, so last thing to compute in here is consumer surplus at the Nash equilibrium. Remember the definition as well. It is the difference between all the marginal willingness to pay, so the demand function, and the price for all quantities sold. So it'll just be the area of this upper triangle between the demand and the price for all quantities. And remember that you'll have to multiply this by the number of days because we want the yearly consumer surplus. So you multiply this by the height of the triangle, which is 3060, the intercept minus the price. So multiply by the base, which is total quantity sold at the Nash equilibrium, 40,000. We divide this by 2, and this gives us consumer surplus for an entire year, which is $14.6 billion. So that's it. We are done for all the computations in part B. We can now move to part C. All right, so part C shouldn't be too complicated either because we have built everything to answer this. So suppose that EasyJet executives have approached Aero Canada's executives with a proposal to form a cartel that will maximize industry's profits in this market. So you are Aero Canada and you have to decide on how to respond to this cartel's proposal. So what is your best response as Aero Canada to EasyJet selling its part of the cartel's number of tickets? So we want to find Aero Canada's best response to some quantity produced by EastJet. And of course, as I said, we already have a function for that. We have from part a best response function for Aero Canada given what EastJet produces. So this won't be too hard to answer. We just have to find what EastJet is going to produce, and then we'll know very easily what is going to be the best response of Aero Canada. All right, so since we know that it's EastJet's idea to form a cartel, once you see this word that we are making a cartel in this market, it should tell you that this company, EastJet, wants to form a cartel to produce the monopoly's quantity and to set the monopoly price because it knows that total producer surplus, total profits are maximized when there's only one firm in the market. So EastJet wants to replicate this equilibrium by forming a cartel and producing the monopoly's quantity and the monopoly price. But this you know how to solve very easily. You know that a monopoly also sets marginal revenue equal to marginal cost, and a monopoly will face a demand function that is the entire demand function for the market with one quantity produced by one single firm. So we won't need a marginal revenue function with two variables anymore. It will just be like a monopoly question. So we'll just use the twice as steep rule to get our marginal revenue function. Remember, we'll get the same intercept. The only thing that is going to change is multiply the slope of the demand function by 2. So we get 3000 minus Q divided by 10 is the marginal revenue function for a monopoly. We set that equal to the marginal cost, which is 60. So we just have to solve for the quantity in order to get the quantity that a cartel would produce. So we can start by subtracting 3060 both sides and multiplying by -1. We get that quantity of the cartel divided by 2 is equal to 3000. And to solve for Q, we can just multiply both sides by 10. So we get that the cartel's quantity is equal to 30,000 tickets sold in one day. And you can see that this quantity that would be produced by a functioning cartel would be lower than what is produced under a duopoly. This is in order to get a higher price than what the duopoly would set, and they would get a higher profit together. But of course, you know that this is not a Nash equilibrium, and we'll see in one moment why this is the case. But we start by assuming that EastJet is selling its part of the cartel's number of tickets. So we are saying that EastJet is selling half of the monopoly's quantity. So we know that EastJet at this moment is selling 15,000 tickets only. That is by assumption. And we will now find Aero Canada's best response to that. And like I said, we already built a whole best response function for this company. We did this in part A. We know that the best response for Aero Canada is given by 30,000 minus the quantity that EastJet produces divided by 2. Remember this? This was step number 2 from part A. And we can just substitute this number of tickets that EastJet produces to know what is Aero Canada's best response. So it is 30,000 minus the number of tickets that EastJet sells by dividing the cartel's number of tickets by 2. And we get that the best response from Aero Canada is to actually produce 22,500 tickets instead. So Aero Canada's best response to EastJet is actually not to cooperate and not to produce its own part of the cartel number of tickets and to actually produce a quantity that is much higher in order to maximize its own profit given what EastJet is doing. And this shows exactly why the cartel is not a Nash equilibrium, because both firms wouldn't be best responding to each other if they both produce only half of the cartel's quantity. And we are pretty much done for this entire tutorial. Thank you for listening to this video. Thank you for the semester, and good luck in your final exam.